Welcome to AstroTours. Thank you for joining us today. My name is Martine Logan, and I'm one of the co-directors for this event. Before we begin our announcements, I just want to say the land acknowledgement for Toronto. We would like to acknowledge the sacred land on which the University of Toronto operates. It has been a site of human activity for 15,000 years. This land is the territory of the Huron-Wendat and Petun First Nations, the Seneca, and most recently the Mississaugas of the Credit River. The territory was the subject of the Dish with One Spoon Wampum Belt Covenant, an agreement between the Iroquois Confederacy and Confederacy of the Ojibwe and allied nations to peaceably share and care for the resources around the Great Lakes. Today, the meeting place of Toronto is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work in this community on this territory. Okay, so if it's your first time to AstroTours, I just want to let you know that we do run these tours on the first Thursday of most months, and you can find the information for that on our website or through our social media pages. Our regular visitors will notice that we're in a new room today. We wanted to use this lecture room because it's a bit bigger and it's more accessible, but we welcome your feedback on whether this was a good room to use or not. So in addition to the talk tonight, we'll have some extra activities afterwards. We'll have refreshments and planetarium shows and interactive demos. Unfortunately, the weather is not great tonight, so we can't open the telescopes, but we will have a couple of them available for viewing, so if you want to just take a tour and learn more about the telescopes, you can do that. And I'll explain afterwards how we're going to move over to the next building to get to the activities that will happen afterwards. There are some planetarium tickets remaining for the 9:50 show, so if you didn't get a ticket and you would like one, you can talk to our planetarium ambassadors who I'll point out after the show. AstroTours is organized and run by graduate students in the Department of Astronomy and Astrophysics, and it's also supported by volunteers who are undergraduates and graduates in various departments. And we run this to share our passion for astronomy, so in that vein, we really welcome your feedback. And most of you have been given feedback forms on your way in, so please fill those out. And as a little incentive, we have some cookies up here at the front. At the end, if you bring in your feedback form, you can get a cookie if you'd like. And we also this time have an online feedback form that you can use. I'll put the link up for that at the end, and it's been flashing through here. So if you show us your completed survey page, we can also give you a cookie for that. Okay, so on to the talk. Our speaker tonight is Natalie Price-Jones. She is a fourth-year PhD student in the Department of Astronomy and Astrophysics. She studies stellar chemistry and applications of clustering algorithms to high-dimensional data. When she's not in the office, she can be found doing yoga, playing Dungeons and Dragons, and honing her archery skills. And Natalie was also AstroTours co-director 2 years ago, so we're excited to have her speak here. Please give Natalie a warm welcome.
All right, while I'm switching my slides, maybe people can tell me if you can hear me in the back of the room or if I need to turn up my volume a little more. I'm seeing some thumbs and some ups. Any better? All right, I got some thumbs up. I like the sound of that. Wanted to thank Martine for that great introduction. It's really great to be here with you all tonight, especially for those of you who really trekked through the somewhat icy conditions outside. I'm really glad that you made it to speak with me tonight and to learn a little bit about what I do for my PhD project. I wanted to start with the main image that I've got on my slide here and ask if anyone can help me out with what this is. Hand in the back. It is a galaxy. Do you know which galaxy it is? The Milky Way galaxy. Yeah, this is our best artist's impression of what our galaxy looks like, our galaxy called the Milky Way. We can see the yellow in the center. That's a big collection of stars, older stars that have been alive long enough they've started to cool down a little bit. We can see the blue, younger stars in the spiral arms. Those are so young, they're burning really hot. They get that blue color. The red clouds we see here are places where star formation is still going on. It's actively occurring, so we can't really see it happening through the gas and dust. And the dark areas are actual gas and dust that is not yet forming stars. It just forms these lanes through our galaxy. I mentioned that this was an artist's impression because it's really our best picture based on this image that came out of NASA, an image of what our galaxy probably looks like based on observations that we've made from Earth. And this image on the right combining these two, this one being of the Whirlpool galaxy, a real galaxy that we've taken a photograph of, into this artist's impression. But why am I showing you guys an artist's impression instead of the real thing? It all has to do with the position of the sun in our galaxy. We're not very conveniently located to take a picture of it the way we might like to. The sun's about halfway out from the center, so you can see where I've marked it there. And more importantly, it's in the disk of our galaxy. Our galaxy isn't some big sphere like some galaxies we see in the universe, but instead it's more pancake-shaped. And our sun is embedded in the pancake like a blueberry, right in the middle. When we look at our galaxy from Earth, we don't see this beautiful spiral design. We instead see something a lot more like this. And even to see this, you have to go to a pretty high-quality viewing site where it's very dark and you don't have light pollution from the cities. You can see in the center of this image, that's the center of the galaxy that we were looking at before, those yellow old stars in the middle. They've gotten a bit blocked by dust and gas that are between us and the center of the galaxy. Because we're in the disk, we're looking through all of the material of our galaxy to see the center, and things get in our way. We have a much poorer picture of what our galaxy looks like. This is interesting for me because the question that I'm looking to answer with my thesis work is this: how can we learn more about our galaxy when we're stuck inside it? How can we extrapolate from this image of what we see on the sky to that overall picture that I was looking at before? I'm not the first person to have thought of this question. There are a lot of people approaching this from a lot of different directions. One really popular approach is to do simulations. What I'm showing you here is a simulation that starts 13.5 billion years ago. People doing this simulation track the positions of stars, dust, gas, and even dark matter in computers to produce this image here, which is just showing the starlight for a galaxy that's forming. As we watch this evolve, we can see that galaxy formation is a pretty chaotic process. Things are moving in and out. There's gas flowing into the galaxy in the center, gas getting pushed out in these large explosions. All these areas of blue are where star formation is really picking up speed. And this kind of simulation is really challenging to do because you have to keep track not only of all of the stars in your simulation, but all of the physics that affects them. You can only incorporate the physics that you already know about, and so you better be sure that that's right. And keeping track over such a long time period allows you to watch this evolution occur as it might have for the Milky Way. This is just one galaxy in a suite of simulations that we're trying to produce things that look like the Milky Way. We'll see when this gets to the end that it doesn't look particularly like the picture that I showed you, and that's because we don't know the exact starting conditions of our galaxy. Since we don't know how it began, we can't simulate exactly how our particular galaxy formed, but these kinds of simulations are good to get an idea of how galaxy evolution proceeds in general, overall. But it doesn't give us that specific picture for the Milky Way that we might be looking for. We can take a different approach then. We can let this galaxy just finish spinning out that last chaotic merger, adding in more and more stars. You can see the spiral arms in the dust. Let's try something else. This is work done by researchers a few years ago now, in 2013. And what these researchers did is they wanted to look out at actual images of galaxies. Everything I'm showing you here is a picture of an actual galaxy taken by the Hubble Space Telescope, and they're organized by their distance away from us. So galaxies on the left, I put 0 light years. That doesn't mean they're exactly in our backyard, but it means they're pretty much right in our neighborhood. Those galaxies we see today, and as we look further out, up to 19 billion light years away, we're not only seeing different kinds of galaxies, but we're seeing older galaxies. Because a light year is the distance that light travels in 1 year, as we look out in distance, we're looking back in time. We're seeing how galaxies looked when that light was emitted, but it takes so much time for that light to reach us that we're seeing a snapshot of the past. You can kind of get a sense for that here. The galaxies on the right side of this image are kind of small. They're a little more blue colored. They're blobby. They're overall different from the galaxies on the right. And what these researchers wanted to do was find out how, in general, galaxies are evolving. Much like that simulation I showed you, they wanted the overall picture. They looked out for galaxies that could have been progenitors for the Milky Way galaxy as we know it, to try and understand how the number of stars evolves over time, how the gas content of a galaxy might change over time. These are questions we can answer to get an overall picture, again, of galaxy formation, but it doesn't really address the thing that I'm most curious about, which is our galaxy specifically. We're going to now go to the approach that I like to take to this question of how did the Milky Way get to where it is today? This simulation I'm showing you is using real data from the Gaia satellite. This is a space-borne telescope that's looking at the stars in the Milky Way, and it's measuring how they're moving. Every dot in the simulation that's moving is moving based on the measurements we've made for how it's moving today, but allowing a lot more time to pass. My approach essentially is to do a case study of the Milky Way, to study it in really great detail, because this is the only galaxy where we can really do that. We can make some observations of our neighbor, Andromeda, which is another large spiral galaxy that's a lot like the Milky Way. But only in the Milky Way can we go to these really high levels of detail, really understand not just what the galaxy is doing as a whole, but what the individual stars are doing to contribute to that whole picture. There's a name for this field, and it's called Galactic Archaeology. It's studying the individual stars, the small scales, to try and make extrapolations about what happened in the history of our galaxy. We all know that Indiana Jones is perhaps not the best representative of archaeology. He's not a great representative for galactic archaeology either. My work is a lot less with golden idols and a lot more staring at the sky. I'd shown you a different picture of the sky before. In this one, the stars are wiggling because they move in position as the Earth rotates around the sun. It's not that the stars are moving overall, it's that as we orbit around our sun, we see them appear to move against the background of the sky. My work is staring at those individual stars and trying to learn more about them, trying to understand them in greater detail. What I'm most interested in is finding stellar siblings, finding stars that are related to each other, that were born in the same place at about the same time. To understand the kinds of clues that I look for, I wanted to make an analogy to actual siblings. This is a picture of me and my sister. I had to point it out because a lot of people got confused about which one I was. There was a suggestion that I might have a brother, but alas, I had an unfortunate haircut as a child. That is me. When we were younger, this is taken when I was 7 at Disneyland. When we were younger, it was pretty easy to tell that we were siblings for some pretty easy reasons. You would see us out together. We grew up in the same place. We were close to the same age. We went to the same school. If we were out, we were probably out with our parents. All of these were nice cultural clues. You could easily figure out that we were siblings. But since I was 7, some things have changed, and not just my haircut. For one thing, we've moved across the globe. I'm still here in North America, but my sister has moved to France. If you met us today, you would meet us separately. You wouldn't encounter us together because we're on different continents. It would be a lot harder to tell that we were related, but there are some ways that you could still figure it out. If you're just observing from afar, it's quite difficult. Certainly you could ask us what our names are. That would be a clue. You have a reasonably unusual name. Stars, you definitely can't ask the name, so that's a little more challenging, and I'm not sure what a star naming convention would be. We could try and go in another direction. One way that you could tell that we were siblings, without even talking to us, would be to do a DNA test, to look at our DNA and see that we were related. So this brings me to a question for my research. If I want to figure out which stars are related to each other, what do I use for DNA? To figure that out, we're going to look at another simulation that I want to just quickly introduce. Before, I was showing simulations of whole galaxies moving at a time. But what I want to look at now is how stars are born. I'm hoping that looking at this process will give me some clues as to what I could use to be a star's DNA. This simulation is keeping track of gas. So this is a big cloud of gas, this big orange thing that I'm showing on the screen. It kind of looks like a star in that it's a sphere and stars are spheres, but it's not. It's much larger. It's got about 5,000 solar masses. It's 5,000 times the mass of our sun. In this simulation, we're going to let this gas evolve according to all the physics we understand that should let gas interact with itself, and watch what happens. As we get these yellow spots in the center, that's showing you places where the gas is becoming even more dense. So yellow here means really high density areas of gas. It immediately forms this kind of filamentary structure. It doesn't stay as a sphere, and that's because the gas is collapsing, becoming denser and denser. It's mostly made of hydrogen, but it's got a smattering of heavier elements in there. Astronomers think that anything heavier than hydrogen is heavy, so we're talking about helium, we're talking about carbon and oxygen. And you can see now these little white dots starting to form. Those are the densest part of all. Those are the stars forming. What we're forming here is a star cluster. These are all the stars that I might be looking for as siblings. They're stars that are being born from the same initial cloud of gas, and they're being born at roughly the same time. The time scale for this simulation is about 200,000 years. That's certainly a big age gap for humans, but it's only about 0.1% the total age of the Milky Way galaxy. So in stellar terms, this is just a snap of the fingers. We're going to zoom out now and look at this cluster, and you can see that some of the stars have moved pretty far away from where they formed. They formed in these yellow regions, these high density areas, but they've since kind of escaped and started to move outwards. The question is then, what do we use about these stars to determine that they were all related, especially the ones that have escaped? It's easy to look at a cluster of stars and say, those stars are in a cluster, so they were probably born from the same gas cloud. But if stars escape, how do we trace them back to their origins? How do we know that they have siblings here in the middle? I mentioned earlier on the composition of this cloud, and you can see that our simulations are reasonably accurate. We look out into the galaxy with the Hubble Space Telescope, and we see regions like this. We can look at what those regions are made of, and we see that they're made of mostly the same stuff as stars, mostly hydrogen and helium. We see the filamentary structures here. It's a little less bright than the simulation I showed, and that's mostly because the stuff in the simulation we were keeping track of as light-colored things blocks starlight. The gas gets in the way of the starlight, and it makes it harder to see. So you get these dark regions instead. This is, again, a snapshot, so it takes 200,000 years for that star formation to happen. So when we look at a place that's actively forming stars, like this Orion Nebula, we're only seeing just a moment in time from that simulation. We can't see what's going to happen in the future there. We can look elsewhere in the galaxy for clues to what that looks like. You'll remember I said in the beginning we had those blue regions of the galaxy. That's where we had young stars because they burn hot and blue. This is an image of the Pleiades, which is a young cluster. And so the stars in it are burning hot and blue. And again, the Pleiades, we can look at them and say, oh, those stars are in a cluster. We know that they're siblings already. It's easy. It's like me and my sister at 7. You can figure out that we're related mostly because we're always in the same place. So how do we find the things that are related to a cluster of stars like this, but have since departed across the galaxy? This is the main focus of my research, and it's called chemical tagging. I mentioned the chemistry of the cloud because all of the stars coming from the same cloud are going to have the same chemical signature. If I look out at the stars and discern their chemical signature, I can say something about which stars are most likely to be related. I mentioned hydrogen and helium, but we try and make use of as much of the periodic table as we can. The more elements we can measure from a star, the better we can understand its specific chemical signature and relate it to other stars in the galaxy. We want to be able to look at the whole galaxy and understand where each individual star came from, find its siblings. So how do we measure the chemistry of a star? Well, we have to start by observing the star. And in the case of the star I'm showing on this slide, it's pretty easy. Does anyone recognize this star? It's the sun. It's hopefully easy to remember because we can actually see it in detail. We can resolve it spatially. We can see these granulations. That's where convection is occurring, the hot stuff rising to the top, the cool stuff going down to the bottom. We can see little magnetic flares coming out, the sunspots that appear light in this image but dark when you look at the sun with your eyes. And this is a really lovely picture. If we could get an image like this for most stars, it would be easy. But of course, when we look at stars, we don't see this nice, big, resolved space. We see something more like that. Everyone sees my little dot? It gets harder. It gets a little bit harder. So we're going to look at that little dot, but what can we possibly learn from our little dot? We definitely get starlight from our dot. And we want to break that starlight down into something that can tell us something interesting about the star it came from. The easiest way to do that is to split up the light into its different colors. I'm showing an example with a prism because it's definitely one you can do just with sunlight on a nice day. You can put your prism and see the light split into that beautiful rainbow of colors. Generally, I use something a little more complicated called a diffraction grating to do this, but the principle is the same. All I'm doing is splitting the light into its different colors, finding that rainbow. And then because I don't want to try and do all of my analysis with my eyes, I take a picture. Same kind of device that takes a picture in your phone is the same thing that we use to take pictures of the rainbow of starlight. Sadly, I don't get to look at these things in color because what I'm interested in is not necessarily the color of the light coming from the star, but how bright each individual color is. When I take a picture like this, I get something called a spectrum, and I'm showing an example here. On the x-axis here, I'm showing the wavelength of the light. The longer the wavelength of the light, the redder the color is. And actually, these wavelengths are so red that they're outside of human vision. There's a reason that we use these particular colors that I can talk about, but essentially, redder is on the right side right now. On the y-axis, we have the brightness of the light at each individual wavelength. And we've gotten very precise with this. We can see very tiny little dips, these stronger features in the middle. And that's because we've taken a really high resolution spectrum. We split the light into more and more and more colors, trying to get really, really fine measurements at each wavelength, and as many wavelengths as we can. I'm going to show you guys a simple example to sort of illustrate what we do to figure out the chemistry of a star, and then go to a bit of a larger spectrum. So this is just two small chunks of a spectrum that I might look at. The important thing for me is these little dips. They're important because we can match them to chemical elements. We know that different chemical elements prefer to absorb different colors of light, so they absorb at a particular wavelength. This star might have started out with being the same brightness at every single wavelength. But instead, because it contains chemical elements, at certain wavelengths, you see these dips. You have less light there because those chemical elements absorbed some of the light that would have otherwise come to you at that wavelength. I can actually figure out which elements are associated with each line. And the way I do that is just by looking at the elements in a lab and comparing them to what I see in the star. So we do all these experiments in earthbound labs, and then we look at the starlight to figure out which elements we're interested in. What I'm showing you here are some of those heavy elements I talked about. We've got a couple of calcium lines, an iron line, and a silicon line. So each dip is associated with light being absorbed by a particular element. We can look at this in a little bit of a different way by zooming in on a section of a star. So here I've taken that box, imagining that we could see the star and actually resolve it spatially, see the surface. We're zooming in all the way to the level that we could see individual atoms, so I can make this little cartoon analogy of what's going on in the star, why we're seeing this spectrum. At the center of the star, this sort of off-screen, that's where the nuclear fusion is happening. So stars are fusing hydrogen into helium. That creates energy, and that energy is escaping as light from the inside. So we've got light that wants to get out. In this star, we have three main types of atoms. We have silicon, calcium, and iron. There are different colored dots here. And you can see right away that the light's going to have a bit of a hard time getting out. As it tries to escape the star, it's going to encounter these atoms. And when it does, it's going to be absorbed at certain wavelengths. We're going to end up with that spectrum. I find it kind of hard to look at this and just kind of understand, so I made a few animations to talk about what I'm doing. In this one, I'm going to change just the amount of silicon that we have in the star and watch what happens to the spectrum. So as expected, as we add more silicon, there's less and less light at the wavelength that silicon likes to absorb. So we have this light that's coming out from the center, but as we add more silicon atoms, it's more and more likely to encounter one of those atoms and have that part of its light absorbed, have that wavelength preferentially dip down. So we should be able to do the same thing for calcium, and indeed, when we do, we see that the calcium lines dip lower. So you can kind of get a picture from this of how astronomers might look at a spectrum and figure out what a star is made of. You figure out how deep the lines are, and then from that you determine what amount of silicon, what amount of calcium atoms you have in your star. So let's ruin that by doing iron. Iron definitely changes the iron line, but it also changes everything else in the star. And that's because the picture is a little bit more complicated than I've let on. There are factors about the star and the way the light travels through it that are affected by the elements in it beyond just these lines coming out. It's actually even worse than this, because at least iron is still a chemical element. In this, I'm not going to change any of the amounts of atoms, I'm just going to change how hot the star is. When I change that, I'm going from a reddish, cool star to a much brighter yellow star, because the temperature is going to determine what color the star appears to be. I mentioned this a few times already, but we get these blue stars. They're really young, they're burning really, really hot. The red stars, they might be young, but they're not big enough to burn hot, or there's some other reason that they're cooler on the surface, and so they end up looking a little different. You can see again that as I change the temperature, we're affecting the whole spectrum. We're changing how everything behaves. When we go to the hotter wavelengths, the lines get smaller, and as we go down to the cooler wavelengths, the lines get deeper, but it's affecting all of the lines equally. I'm pointing this out because I wanted to make you aware that you have to be a bit careful when you're interpreting these spectra. It's sadly not quite so simple as just looking at how deep the lines are. You do have to account for these other factors, like the temperature of the star or how much iron it's got. But let's assume that we're pro-astronomers and we can mostly take care of this, or better yet, rely on people in the past who have figured out good ways to take care of this, which is my personal strategy for my thesis. Stand on the shoulders of giants. We might get something like this. I was showing you a single spectrum before, and now I'm showing you 50 examples. This is real data taken by the Apogee survey from a telescope in New Mexico. I'm showing, again, wavelength on the x-axis here, and I've actually changed the brightness of each star a little bit just so that you can see the differences between the spectra a little bit better. So it's not that this star at the top is the brightest, I've artificially added a bit of a difference. Because what I want to do now is quickly look at these stars and figure out which ones the siblings are, which should be easy, I hope. Everyone knows which ones the siblings are? No one said yes, which is good, because that means I can finish my thesis. Thank you. If you could do it just by eye, please come talk to me, because we need to write that up ASAP. What you can see when you compare these spectra is they all have the same kinds of wiggles. So they have those absorption lines I was talking about before, from elements taking away parts of the light at certain points of the spectrum. Some of them have unique wiggles. Some of them have more of a wiggle than others, so maybe that tells you something about the abundances. But it's obviously pretty hard to look at just these 50 spectra and make some assessment about which ones are similar to each other. Let's make it a little bit easier. Instead of trying to compare all of the different wavelengths at once, let's just pick 2 wavelengths and look at those. Okay, so I'm looking now at the brightness at my wavelength A versus the brightness at my wavelength B. What I want to do is change my spectra in a way. The spectra with 200 different wavelength measurements are pretty complicated, and they're difficult to look at and compare. What I'd like to do is reduce the dimensionality of those spectra. So that's that high dimensional stuff that really got you in my abstract. You were like, I got to learn more about this high dimensional astronomy she's talking about. And maybe it's slightly less exciting when you see this. What I'm going to do is reduce from 2 dimensions down to 1 dimension. And one way I can do that is projecting the data onto a line. So here, the yellow points are how the purple points would be if I projected them onto that line that's rotating through. And I've got a lot of different choices for which line to use. So the question is, which one do I pick? I could pick the straight up and down line, but that kind of mushes all my points together in the middle. It's hard to tell them apart. What I want to do is pick a line that maximizes the difference between the different points. I want to keep track of the fact that the stars are different. I don't want to mush them together. I want to keep them spread out. So you can see that maybe something close to the horizontal might be the right choice, maybe a little bit off. The technique I'm going to use to figure out which exact line to use is called principal component analysis, and it has rules. It says you have to pick the line along which the data are the most varied, the biggest difference in the data exists. And it also has a rule for figuring out exactly what line that should be. Easy. I can just tell you that it should be this line, and I've taken 2-dimensional data and transformed it down to a single dimension. Okay, that's not so exciting. It's a little bit easier to look at than high-dimensional data, but I can do the same thing with all of my 200 different wavelengths. Instead of just looking at A and B, I can look at the whole spectrum and change it from 200 wavelength measurements down to just 2 different dimensions. When I do that, I get the lines that I need to use to project my data on. These are what I call my principal components. And these principal components look in some ways a little bit like the wiggles on the left-hand side. They're not super informative. I can see that in some cases they're highlighting places where the spectra have wiggles, and that's because of my rule about what the principal component should be. It has to pick the places in the spectrum that is going to maximize the difference between the stars. The second principal component is really picking out some unique feature. It wants to tell me about a single star. All right. I can project into those 2 principal components, and now the colors of the dots are the same as the colors of the spectra on the left. Again, we're not immediately able to pick out any siblings because we'd expect siblings to be really close together in this plot on the right-hand side. But unfortunately, with this many stars, they're just kind of sitting on top of each other. There's a couple things that sit away from the rest of the stars, and that might be interesting to examine those stars as being chemically peculiar, unique stars that we might be slightly more inclined to learn more about. But they're not telling us about siblings. And the main reason that we don't get to learn anything about siblings from this is that we're only looking at 50 stars. 50 seems like a lot when you have to compare them by eye, but in reality, the Apogee survey, where that data came from, is observing 200,000 stars overall. The contours on this left-hand plot are showing you where the Apogee survey looked, and you could actually use that to figure out where the sun is, because it observed the most stars just about there, and it's easiest to look at stars near the sun. 200,000 stars seems like a lot overall. It gets even worse because people won't stop going towards the future. In 2025, there's a planned mission that has 4 million stars. This is actually really good for finding siblings because when we only had 50 stars, we actually had really low odds of picking any 2 stars that came from the same birthplace, especially because they're scattered across the sky. A star cluster can range in size from having only 30 members to having over 10 million members. But if we're looking at one of the small ones, just 50 stars is not going to be anywhere near enough to find any siblings. So it's good that we have this much data, but we have to be able to process it. We have to understand how to use it properly. To do that, I've been creating some simulations. Sadly, my simulations don't look quite as cool as those galaxy evolution ones, but I'm going to try and sway you over anyway. I wrote down the steps just in case I bonk my head on the way out of here and forget how to do my thesis. I can always refer back to these simple 6 steps to create a simulation to test whether chemical tagging will actually work. Step 1, make a lot of stars. We have good examples of how to do that. We have observed a lot of stars, so I'm pretty confident I can make realistic stars. I'm going to give each star a mass, so somewhere from about half the size of our sun to about 10 times the size of our sun. And much like star clusters, it's pretty preferred for stars to be small. So I'm going to make a lot more small stars than I am going to make big ones. Big stars are rare. I'm then going to distribute them into clusters. Again, I'm going to make more small clusters than big clusters because we know from observing clusters in the Milky Way that we've got more small ones than big ones. Each cluster is going to get all its members the same chemistry. That's that rule I set out at the beginning. If I want to be able to find the siblings, I need to use their DNA, so I better give them the same DNA to start with, or I'm definitely never going to find them. Then I give each star a spectrum, like the spectra I was showing you before. I want to give each one something that I could have observed from a telescope. And because I'm observing it from a telescope, I want to add a bit of noise, a little bit of uncertainty. I want to say I don't know exactly how bright that star was at that particular wavelength because maybe there was a cloud in the Earth's atmosphere that day and it kind of interfered with my measurements. Or maybe there was some interstellar dust between me and that star and it interfered with my measurements. These things can have a pretty profound effect, so I want to include them in my simulation so that I know I'm doing the right test to determine whether this process is actually going to work, whether I can really find the siblings in real data. This is the kind of data I work with. I promise I'm not going to show this for too long because it's kind of horrible to look at. But you can see now we've gone from the 50 stars that we were looking at before to 50,000 spectra. There's so many of them, I had to really squish them together and just use the color to tell you how bright the star is at each of the wavelengths that are here along the x-axis. So blue here means that it's brighter at that wavelength, but now you can really see that there's no way that I could look at this by eye and find the siblings. Like, unless I was willing to compare each pair of stars sequentially and spend about, I don't know, 30 years doing my thesis, I can't do it that way. I really have to use this dimensionality reduction to change this massive, horrible thing into this. This is much easier to look at. And unlike the sample of 50 stars that we looked at before, we can actually start to see a bit of structure in this space. We can see some things that might be associated. I'll do some circles. So by eye, 2 days ago when I was making this slide, these were the clusters that I thought I could find if I just looked at this slide. So my guess is that since these things are close to each other in this space where I projected onto two principal components, they're probably chemically similar. They're probably stellar siblings. But there's this big mess in the middle, and like maybe this one is a cluster, but I'm not quite sure. So I need a better approach to figure out what the siblings should be. The way I'm going to do that is with an algorithm called density-based spatial clustering applications with noise. I had to read that off my slide because basically since I first found out about it, I've been calling it dbScan, which is, it just rolls off the tongue. It's got scan in it, which sort of implies that it's looking for things. I really like the name. dbScan classifies your stars into 3 different types. You can have a core star. That's something that's really at the center of a cluster. You can have a border star, or you can have a noise star. The way it does this is you tell dbScan, I want you to look in this size neighborhood, and I want you to look for, let's say, 7 neighbors. If you find 7 neighbors in the neighborhood, then that's enough stars that I'm interested in that cluster, so you're going to call that a core star. Anything that's in the neighborhood of a core star but isn't itself a core star gets to be a border star. So it's sort of on the edges of the group, but it still gets to be like part of the neighborhood. We still get to include it. And anything that's way outside gets to be a noise star. This is really helpful because, as I mentioned, for some clusters, they're really small, and we're not expecting to see many members. I only want to find clusters that are big enough I can find several stellar siblings, because it's interesting to me to study multiple stars at once. So having this designation of saying, there are some stars out there, they were probably part of a group, but they're not near any groups, just ignore them. They're just noise. I'm not interested. To show how this works, I'm just going to make some more fake data. By eye, you can probably figure out where the clusters are, because this is only in 2 dimensions. You can see that I've put 3 in here. There's a bunch of other stars around, but maybe those are the noise stars. What dbScan is going to do is it's drawing that circle around every star, and it's saying how many stars are inside the circle. If there are enough stars inside the circle, then that's a core star. And if there aren't, I'm going to call it either a border star or a noise star. So we just algorithmically go through every single star and check whether it meets our criteria. Once we've done that, we get a set of core stars. And that actually looks pretty good. That matches pretty closely to the data I put in. We get the purple group, the yellow group, this brown color. It looks better on my computer, but we're going to call it brown. We get these core stars. And when we go to the next slide, we can see that there's these navy points. dbScan has thrown those away as noise, and it's added a few border stars to these main clusters. So you can see pretty clearly how it works in 2 dimensions. And the biggest advantage of this approach is I didn't have to tell dbScan how many clusters I was looking for. Sometimes, if I just look at this data, I know that it should find 3 clusters. But if I'm looking at high-dimensional data where I've taken observations of the galaxy, I don't know how many clusters there are to start. So this algorithm is super powerful for helping me figure that out. So if we go back to our data here, we can color code it by the groups that dbScan found. And you can see that dbScan agreed with some of my groups. It didn't love this group. It put those stars in a lot of different colors, so a lot of different clusters. It split this one up into 2, where I had it as 1. But I did all right with a few of them. I definitely didn't find any of this stuff in the middle, though, and that's where dbScan was really powerful. It was able to distinguish those clusters that are in the middle of this messy-looking data. This color coding is the true clusters that I had originally given. You can see that there's a lot more of them, first of all. There's about 15,000 clusters that I started with, and only 1,600 were found by dbScan. That's not as bad as it sounds. I mean, I know it sounds bad, But it's not terrible because, as I mentioned, we had all those noise stars, and DBScan just throws those stars away. They all get put into the same bin. We throw them in the trash. We don't count them as clusters, and so that really reduces the number of clusters we get overall. If I go back here, you can see that, again, I did roughly correctly just by eye, but DBScan did do better. It got closer to the original data that I put in. So it's good at recovering the clusters. So what does this mean? I can find these clusters. All of the members are presumably stellar siblings. What does that actually tell us? Well, I want to go back to the simulation that I had at the beginning, because the real key that I was trying to get to is understanding the Milky Way's history. Not just the history of a simulated galaxy that's like the Milky Way, although that's very useful for understanding in broad strokes. I wanted to understand the Milky Way specifically. I wanted to understand how many of these chaotic merger events happened in the Milky Way. When did the most star formation occur? And these are the kinds of questions that chemical tagging can answer. When we find the stellar siblings, we find a group of stars that were born in the same place at the same time. We know something about their ages. We can figure out ages for stars across the galaxy. We can determine how much star formation was happening and when. The chemical changes in the galaxy overall evolve with time. The chemical signatures of these clusters, the DNA of the stars, is changing as stars grow and evolve. And we see these mergers with other galaxies. This is an example of the Antenna Galaxy. It's, again, a real image taken by the Hubble Space Telescope. And that's somewhere out in our universe. It might have been in the Milky Way's past. And more importantly, understanding this past might tell us something about how the Milky Way will evolve in the future. We know that the Milky Way is on a collision course with a neighboring galaxy. This might lend us insight into how the Milky Way recovers after an event like that. I wanted to leave you here with this image. It's not an image, it's a video. And it's because I really think that this is the most powerful thing we can be doing with our observations of the Milky Way. This is the best galaxy to do this kind of case study, to really get close to the data and understand what's happening on the really small scales to get an understanding of what the big picture should be. This is from a gravity collaboration that was looking at the center of the galaxy, but I think it's a really powerful image of how far we can go all the way looking through all of these stars to get to the individual level, to keep track of what the individual stars are doing. And as we get closer and closer to the center, we have more and more power to learn about not only where our galaxy has been, but where it's going in the future, and what we can expect for other galaxies. I'm going to let us come back out to Earth, back to that image, and take your questions now. Yes?
So you're saying that the clouds that the stars form from, they're mostly hydrogen and helium, right?
Mm-hmm.
So why would it be that the stars that get formed from that would have the same chemical signature as each other? Like the chemicals are being formed inside the star, I think?
This is a great question. So the question was, if the cloud that forms the stars is mostly made out of hydrogen and helium, then how do we get chemical signatures that are the same if some of the elements are formed inside the star? So while that cloud is mostly hydrogen and helium, it's not entirely hydrogen and helium, and that's important. So the trace amounts of other elements in that cloud are what's going to give that particular cluster its chemical signature. Even more important is the question of what happens to the elements that form inside the star. So we had nuclear fusion that fuses lighter elements into heavier elements. And this would be really crucial to changing the signature of a star over its lifetime. But while there's convection inside stars, you don't get a lot of motion of stuff from the core making it all the way to the outside. Light can travel out, but the actual atoms don't mix very well. This is actually a challenge with some older stars. They're called red giant stars. There is some mixing there because they have really vigorous convection zones that extend a long way. But for most stars, they never mix the stuff that they make in the center with the stuff on the outside. So they keep that pristine chemical signature from when they were born, just because of those trace elements. Hydrogen and helium are a big component, but we don't look at those elements. We look for the traces of the heavier stuff. Yeah? Mm-hmm.
Have any stars been found that may be siblings of our own sun?
This is a great question. Are there siblings of the sun? And it's probably how this field got started. It's called the search for the solar twins. So not even just siblings, but people are looking for things that are exactly the same because they want to find the cluster that the sun was born in for, I think, fairly obvious reasons. The sun is obviously the best star. So there have been a lot of solar twins found. It's just a question of how much you want your chemical abundances to be exactly the same. So we talked about there's this uncertainty when we measure the spectra of the star that can come from a lot of different sources. And so to the level of that uncertainty, we have found solar twins. But we're not sure if they just look the same because there's a bit of a fudge in our measurements or because they're actually the same. But it's a really hot area of research. Yes?
Why, if stars were born in the same cluster, do they start moving in other directions? And if they move in other directions, can that affect their chemical composition?
Great, yeah. So if stars all get born together, why do they spread apart, and does that have any impact on their chemical composition? So the reason that they get spread apart, we sort of saw a bit in that simulation, but it's kind of hard because it's going pretty fast. Essentially, you have these gravitational interactions. And so a gravitational interaction between two things is pretty stable. They'll just kind of orbit each other at some good radius. But once you add a third thing in, it becomes chaotic. It's the three-body problem of how do you predict what's going to happen. And sometimes what happens in those systems is one star gets a huge kick and moves out. So that's one way that can happen. You can end up with a nice stable cluster that just moves along happily, but unfortunately, unlike in that simulation, the star cluster is moving through the Milky Way, where we saw there were those big spiral arms, there's lots of other stars, there's other gas clouds forming other clusters, and all of these things have the power to gravitationally grab one of the stars or kick one out in the way that the three-body problem does. Fortunately, none of those things change the chemistry of the star, though. That's why we use chemistry as the marker. The star's position and its speed might change over time, but the chemistry stays the same, except in the exceptions that I was mentioning in answer to an earlier question. I had one over here, I think. Yeah?
What causes the spinning motion to happen, like on your original videos? You started off sort of globular and going in every direction, then it came the spinning motion.
The one of the galaxy evolution?
Yeah.
Okay, yeah. Why is the galaxy spinning in that simulation I showed where the galaxy is forming over time? And the answer there has a lot to do with its shape, because you start out with this nice spherical, you couldn't see the spherical ball of stuff because it was mostly gas when it was starting. But as time goes on, it gets maybe a little kick and it starts to rotate in some direction through a gravitational interaction with another forming galaxy or with a clump of dark matter. These are all examples of things that can cause that. Once you get that kick started, it's all kind of over because the thing that was once spherical starts to collapse into the pancake shape, and the pancake shape is very, very good at spinning. It conserves its angular momentum. So angular momentum is just how much you want to spin. When you're a sphere, you can spread out that angular momentum over the whole sphere, and it's pretty easy to just keep spinning. But as you squish down into the pancake shape, you get a lot more spin. So even starting out with a little bit of rotation in the sphere gets squished into the pancake, a lot of rotation.
It concentrates the spin.
Yeah, it concentrates the spin because of the change in shape. Yes?
You mentioned how for iron it's a bit of an unknown, a strange thing, how it changes everything. So what makes certain things affect only its spectrum, and what makes other things affect their spectrum? I believe, if I'm correct me wrong, that the fingerprints are taken from emission spectra on Earth. Is that correct?
Yes, so the fingerprints on Earth, when we figure it in the lab, those are taken from emission spectra of those elements. And the question was, why is iron so poorly behaved? And I'll tell you a secret. It's that I cheated a little bit. Because if you'd been watching closely, you'd see that the silicon and calcium also affected the whole spectrum. It's just with them, the effect is much less pronounced. These plots are really big. There we go. Please give me pass. I wanted to give you a chance to watch this again. Well, thanks for that, I guess. All right. Let's go back and watch them one more time. All right. You gotta watch pretty closely. But you can see there's a little tail moving over here. There's a bit of a wiggle happening over here. It's much less obvious, and I didn't call attention to it when it's happening, but all of the elements kind of have this effect. Changing the overall atmosphere of the star has these kinds of effects. It's just that, you get the wiggles over here. Iron is the most pronounced example of this. And I can talk to you a little bit about the reason for that afterwards if you like. I'll just leave that up. I think I have time for one more before I have to let them do announcements, so yes.
The spectra, you said that the stellar diversity is eject all these stars within about, what, 2.5 million years or something like that?
200,000 million years is about the timescale.
Well, it's short in the lifetime of the star anyway.
For sure.
So since all the stars are basically the same age, they'd all be at the same stage of development, so would that be an influence in their spectra?
Yeah, so the question is, can you just look at where the star is in terms of its evolution, its overall lifetime, and figure out from the age which stars should be from the same cluster? And the problem there is that you could totally do that, but only if all the stars were the same mass. As stars are born more massive, they evolve faster. So you have to take into account the mass of the star when figuring out the age, and it's difficult to measure the mass of the star directly. So for example, a really massive star might have a lifetime of only like a couple 100 million years, just about the time it takes to form, whereas a really low mass star, I mean, our sun lasts for 10 billion years, but there are low mass stars that we expect to outlive the total age of the galaxy, for example. So looking at the stage of evolution is not enough because you need to know also something about the mass of the star to figure that out. That was a really good question though, thank you. I think I'm going to let Martine take it away, and thank you one more time for being such a great audience.